All right, so in this video series, we are going to be deriving the C6h character table. And so I've gone through and I've done the other CNH character tables with n being less than 6, greater than or greater than 1. And so a lot of these same sort of patterns are going to emerge here for this character table, but there's more symmetry operations. Here's an example of a molecule we could use to visualize. But basically what we know is that there's going to be a C6, and you can see that in this molecule here. A C6 is, of course, a 60-degree rotation. We're going to end up calling that our z-axis. And so is our principal rotation axis, our highest order n in the molecule. And then there's also going to be a sigma h, a horizontal mirror plane that runs perpendicular. That just comes, you can tell that from the name of the point group. And then we're going to have all the symmetry expressions that are sort of derived from those two fundamental, if you want to call them, symmetry operations. So, of course, there's always identity. Our first task in deriving the character table, as always, is to come up with all the different symmetry operations. There's going to be that C6, that 60-degree rotation. Then you can do a C6 twice. That's going to be equal to a 120-degree rotation, which we could simplify and just call it C3. 360 divided by 3 is 120 degrees. And then moving on, there's going to be a C6 3 times. That's 180 degrees, which is equal to a C2. There's going to be a C6 4 times, which is going to be equal to a C3 twice, 240 degrees. And then there's going to be a C6 5 times. And from there, we also know that there's a sigma h, right? There's no C6 6 times, by the way, because that equals identity. And from here, we can start kind of deriving other symmetry elements that are mathematically unique using sigma h. So the way that we can do that is, well, we know we have a C6, and so we can do improper rotation axes. So C6 operation followed by sigma h, that's the definition of a S6. So you're going to do a 60-degree turn, so that will turn this methyl group. Well, let's always do it the way we do it, which would go the other way. That would take, let's see, this methyl group, put it to this methyl group, and then I'll flip it up above the mirror plane to that methyl group. So that's the sigma h part of it, that last flip up. So that's a unique operation, the S6. We can think about, well, what happens if you do an S6 twice? Well, that's the same thing as doing a C6 twice and then a sigma h twice. Well, sigma h twice is the same thing as identity, doing nothing, because you flip up and then flip back down. So that's just equal to C6 twice, which is equal to C3. We already have that. So anytime you have an even number with these improper rotation axes, you do an improper rotation axis operation an even number of times, you're always going to get just a rotation, because the mirror plane quantity here is just going to cancel each other out and be an identity. So we can just go on to just evaluate the odd versions of these. So what happens if we do an S6 3 times? If we do an S6 3 times, we're going to get a C6 3 times and a sigma h 3 times. Well, if we do a sigma h 3 times, that's equal to a sigma h 1 time, right? We flip down, top went down, down went top, and then top went down. Well, that's the same as just doing top went down. So that's going to be equal to C6 3 sigma h. And C6 3 is going to be 180 degrees rotation, which we set up here, right? It's just a C2. So that's a C2 sigma h. And a C2 sigma h is actually the same thing as the inversion operator. And I have another video that goes through why C2 sigma h is the same thing as inversion. or you could also call this S2. Why S2 is the same thing as inversion. But basically this S3 here we can write as inversion, but that's a unique operation here. So that's a unique operation. So maybe we should start circling our unique ones. We have inversion, we have identity, we have C6, we have C6, 2, which is C3, we have a C2, a C3, 2, a C6, 5, and a sigma H. And beyond that, you know, S6 4 times, that's the even one. We already established that that's not going to be unique. But we could do an S6 5 times. And that's going to be equal to a C6 5 times. And because it's an odd number of sigma H's, it's going to be sigma H 5 times, but that just becomes is equivalent to sigma H. So that's a unique operation that this point group has. And then we can just keep marching along. So S6 6 times, don't have to worry about because that's even. What about S6 7 times? By the way, inversion here, the definition, right, is xy, any arbitrary point xyz goes to negative x, negative y, negative z. So you can kind of check that that's going to be true here. This methyl group, which is at the front bottom right of the molecule, is going to be inverted into the back left behind of the molecule. And so it's the exact opposite. And so that kind of happens. Everything sort of goes to the opposite of what it was. But so yeah, this molecule and all molecules in C6H point group have inversion. Okay, what about S6 7 times? Well, that's equal to a C6 7 times followed by a sigma H 7 times, which is equal to a C6 just once, because C6 6 times is a C6 6 times is equal to identity, and a sigma H is sigma H 7 times equal to sigma H. So this just equals to S6. And so if we go through this, these are we've sort of looped around, right? We already have S6, so let's just circle that. That's one of our unique ones. The only other one that we're missing here is our S3. Well, it's based on S3. So you can see we have S3s in this molecule, right? And how do we know we have an S3? We actually haven't written that down yet, but we know we have C3 and we have C3. So we have to derive that as well, right? We have C3. So we came up with all these. We came up with as many operations as we could based on combining C6 and sigma H. But we can also think about combining C3 and sigma H. And that's actually a unique one that we haven't written down yet. It's a C3 S3 a C3 followed by a sigma H. We don't have that yet. It would also be a C6 2 followed by a sigma H is another way we could have written it. But we didn't have that before we tried S6 2, and that gave us, you know, just a C3 back because of the 2 sigmas. So S3 is going to be a unique one. And then we could think about, all right, well, what if we do an S3 2 times? Well, we know that's an even number, so that's not going to be unique because we can get even number sigma H's. S3 3 times is going to spin us back around to identity because we're going to C3 3 times. S3 4 times isn't unique because it's an even number, but S3 5 times is. S3 5 times is equal to C3 5 times by sigma H, which equals, you know, C3 twice, because C3 3 times is followed by sigma H. So that's unique. Basically, the rotating the opposite way, okay, counterclockwise or clockwise for 120 degrees here, followed by a mirror plane, and here the opposite way, C3 240 degrees. That's going to be unique, S3 5 times. We could do an S3 6 times, and that's going to get us back to identity. So that's no good. And then we can think about, all right, what if we do something generated from the C2? Well, if we do that, C2 times sigma h, that gets us to identity inversion, which we already showed. And then if you move on and try to generate things from C3 you're back to here, okay? And same thing with C6h, you're going to be back to here. So these are all of the operations in the C6h point group. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 operations in this point group. And then the next question is, how do we split these up and group these into classes? Not split them up, but group them into classes. And for the CNH point groups, it turns out each operation is always just in its own class. So here we're going to have 12 classes. And there's reasons for that I've talked about in other videos. Just to remind you what the definition of how do you figure out whether or not you put two operations in the same class? The definition is if you can show that two operations are equivalent, are mathematically equivalent in the transformation that they do, their transformation matrix, for example, when you use two different valid Cartesian coordinate systems, then they may be grouped in the same class if the point group has a symmetry operation that can interconvert those two Cartesian coordinate systems. So you might think here, for example, that like C and a lot of other point groups, C6 and C6h are in the same class, because if you define the Cartesian coordinate system in one way, you might be taking this methyl group and going to that methyl group for C6, and then a C6h takes you all the way around here, right? But if you define the Cartesian coordinate system in the opposite way, you'll get that a C6 once goes here to here, and that's the same as what your C6 5 did when it was defined this way. And so those would be equivalent, but they're only equivalent if there's another symmetry operation in the point group that can interconvert those two Cartesian coordinate systems. Usually what that's going to be is a perpendicular C2, sigma v, or sigma d. And you don't have any of those operations in the CNH point groups. And so for that reason, it's a long-winded way of explaining to you why all 12 of these operations must be placed into separate classes, okay? Identity and inversion are always going to be in their own classes. Mirror plane is pretty obvious that it's going to be in its own class because there aren't any other mirror plane operations. But these proper and improper rotation axes, it's a little bit less clear at first glance, why these all need to be put into separate classes. But that's how it is for this point group, for the CNHs. Okay, so in the next videos, we'll go ahead and start deriving this character table now that we've figured out what the symmetry operations are.